Hello बच्चों in today's video we are going to study earth magnetism and in which today we are covering two topics. The first one is history of the earth magnetism and its origin, and the second one is elements of the earth magnetism. And now first we come at the history. In 600 BC in Greece, the shepherds observed that the shoes that is embedded with the iron nails began to stuck with the earth surface. That was the first proof that explained that the earth also behave like a magnet. And for the confirmation, we suspend a bar magnet freely, and it always come at rest in north-south direction. Means if you suspend a bar magnet in any direction, let's say in east-west direction, then due to the magnetic field of the earth surface, it will automatically come to its direction, that is north-south direction. This is all about the history, and now we are going to move on the origin. The theory that was proposed initially, that explained how Earth behave like a magnet. The first theory was proposed, and it said that there is a large bar magnet inside the Earth that produce that cause the Earth magnetic fields and behavior of the Earth like a magnet. But it was rejected in further years because when we study that at high temperature the magnet began to lose its property, then this theory cannot withstand at that condition. And then there is a second theory come, and it tells that metallic molten fluid inside the earth that contain iron and nickel rotate with the earth at high temperature, and the atom of this metal get ionized and rotating, due to which current develop, and due to the develop of this current, magnetic field develop. This is similar to what we study, the magnetic field due to current carrying coil. As we study there is a coil in which a current is flowing, due to which a magnetic field is developed, as we studied earlier. The Earth's magnetic field similar to this. Now we are moving to the magnetic field lines of the Earth. As here we can see that the magnetic field lines originate from the magnetic south and going towards the magnetic north. And the interesting point here to note that there is two poles. One is magnetic north pole and second one is magnetic geographic north pole. And the angle between these is 11.3 degrees. The magnetic field needle that is vertical at 2 points. As you can see that the one is at magnetic north pole and second one is at magnetic south pole. And the place where north pole of the needle point vertically downward, that is this point. That is the north pole is vertically downward, and this indicating that is this is magnetic north pole, and similarly this is magnetic south pole. And now here we are going to study what is difference between magnetic and geographical equator. The geographical equator is same as we have studied in our geography classes, but in physics there is a difference, and this is magnetic equator that tilt from the geographic equator at 11.3 degrees. And one also interesting point to note here is that there is a difference in the magnetic field in the bar magnet and the magnetic field direction in the earth. In the case of earth, in case of bar magnet, the magnetic field outside is from north to south. As you can draw a bar magnet, and if we mark this as north and this one is as south, then here the outside the direction of magnetic field is from north to south, and inside from south to north. From here, we can see that the magnetic field direction outside of the bar magnet is from north to south, and inside it is from south to north. But in case of Earth, it is reverse. In case of it is from south to north outside and north to south inside. As we can see in this figure, here we can see that the magnetic field direction is from south, magnetic south to magnetic north outside, and it is from magnetic north to magnetic south inside, and the magnetic field is perpendicular at north pole. uh, Now we are going to study the element of the earth magnetism, in which the first one is angle of inclination or angle of dip. Angle of inclination is also called angle of dip, that is denoted by I, and the second one is angle of declination, that is D, and the third one is magnetic field component, that is BV and BH, in which BV is for vertical component of the magnetic field, and the BH is for the horizontal component of the magnetic field. Now let's take a look on angle of dip, that is also called angle of declination, angle of inclination, sorry, that is angle of inclination. Angle of dip, it is the angle made by the dip needle. Mark my word, the angle made by the dip needle in the magnetic meridian. This is very important line. The angle made by the dip needle in the magnetic meridian with the horizontal surface. Since I have not told you yet what is magnetic meridian, so for simplicity, I will draw a diagram that will explain what is angle of dip. Firstly, draw the earth and then the magnetic fields, and then if this is the net magnetic field, if this is R and this is the magnetic field line, then the net magnetic field is drawn by drawing the tangent at the magnetic field line, and the component of it, the total magnetic field is BV and BH, and the angle between the total magnetic field and the vertical component of the magnetic field is the angle of inclination. If I will draw it clearly, then it will look like this. I is this, and BV become this, and BH become this. This will look like that. This is the angle of inclination. Again, this is angle made by the dip needle in the magnetic meridian with the horizontal surface. It will say at this, and now we are going to study angle of declination. Angle of declination, it is the angle between the geographic meridian plane and the magnetic meridian plane at any point of the earth's surface. As you can see from the figure, that this is geographic meridian plane, and this is magnetic meridian plane, and D is the angle between these two planes, that is dip. And as we not study geographic meridian, magnetic meridian, so I will explain you what is geographic meridian. Geographic meridian is that at any point on the earth's surface, the plane that passing through the geographic plane and that point, that is the plane. This is the plane. If you imagine that this is the plane, and at any point in the earth surface, the plane passing through geographic pole, that is if this is geographic pole, that is north pole, and if you suppose any point on this plane, let's suppose here the point is x, then the point that is passing through the geographic pole and that point, then this is geographic meridian. And similarly for magnetic meridian, the plane that is passing through magnetic pole and the point of observation, that is called magnetic meridian. If you write it is Sorry, uh, this point is very below on the board, so I will not able to write clearly, but you can understand it. What is magnetic meridian? That is at any point on the earth surface, then the plane passing through the magnetic pole and that point, this is magnetic meridian. Now I have explained you what is geographic meridian, what is magnetic meridian, so you can easily understand this definition. What is angle of dip? As we told earlier that angle it is angle made by the dip needle in the magnetic meridian. So this is the magnetic meridian plane, and this is the angle made by the net magnetic field, and this is horizontal magnetic field, and the angle made by the total magnetic field and the horizontal magnetic field in the magnetic meridian is called angle of dip. Now something I need to explain is angle of on pole angle of inclination, angle of dip is 90 degree. As we have saw that horizontal surface, if it is like this, then the I is perpendicular to this, that is angle of dip is 90 degree, and on magnetic south pole it is same, that is I is equal to 90 degree, but at equator, that is magnetic equator, I is equal to 0 degree, and same here. And the third component, that is magnetic field component, that is also very important. Now we are going to draw the same like as we draw earlier. Here we draw the magnetic field lines. This is total magnetic field, this is horizontal magnetic field, and this is vertical component of our magnetic field, and this is angle of dip. And if we draw this here, this is angle of inclination, total magnetic field, horizontal magnetic field, vertical magnetic field. Then tan I is equal to dV by dH, and I is equal to tan inverse of dV by dH. This is the formula to find angle of dip. Now we are going to solve one question to clear our concept that we have studied earlier. The question is like in magnetic meridian at a place, the horizontal component of the earth magnetic field is 0.26 cos, and the dip of the angle is 60 degree. Then we have to calculate total magnetic field of the earth, and hence the vertical component of the magnetic field. The question is that we have given the horizontal component of the magnetic field, that is BH. We are given that is solution. We are given BH is equal to 0.26 cos, and the angle of dip I is equal to 60 degree. Then we have to find total magnetic field. Then as we study here that the diagram, that is the horizontal component of magnetic field, vertical component of the magnetic field, and the relation between them, that is I is equal to tan inverse BV by BH. That is now if I take this, that is BH BV then BH is equal to B cos I. Then BH is equal to 0.26 is equal to B and cos of 60 degree. That is 0.26 is equal to B 1 by 2. That is B total is equal to 0.52. This is the total magnetic field, and similarly we are finding the vertical component of the magnetic field, that is by tan of I is equal to BV by BH. From here BV is equal to BH times of tan I, that is BH times of tan 60 degree, and then tan 60 is equal to uh, tan 60 is equal to root 3 and 0.26 into root 3, and the final solution that will come is our answer. Let's see what is the answer. That is 0.26 root 3 gauss. All about in this video. Hope it will be helpful for you. Thank you.